right, welcome back to Project 3. So the big thing that we have is that time only matters on a clock edge. That's a huge important deal. We got all these D flip-flops arranged from gates and stuck them together. The D flip-flop discretizes time to only mattering for an edge. This is the D flip-flop. This is what you're going to actually be using in your project. You have been given a Nand gate, and now we've kind of been hand-waved about it, but essentially you're given a D flip-flop, and the important distinction of the D flip-flop is that you have to have a clock edge. It's going to flop it back and forth. I think the book calls it ticks and talks, and when you transition from a tick to a talk, that's a clock edge. Same thing as a low to high or high to low edge. It's an edge of a clock. Okay, time only matters on those edges, and that's where we're at. So now, let's say we want to store a single bit of data on a clock edge, and of course later recall it. This is going to be the way we can store a single bit. We have some data input right here. It's going to go through our multiplexer because we want to be able to store that bit on a D flip-flop. So this is the input right here going into the D flip-flop. This symbol with a circle, or sorry, I just circled it. This symbol with a triangle, that means a clock. So there actually is another connection called a clock that's connected, and that's going to be connected to everything else in our system. It's just that in this class we don't draw those out explicitly. Just know that's what that means. These triangle means it is rising edge, and that's going to be connected to a clock signal. So we have a D flip-flop. It has an input, it has a clock. So on a clock edge, whatever input here will be placed on the output, and so we then update the output of the bit circuit itself. But there we're going to feed back. So the output of this flip-flop is going to be fed back here to the multiplexer. So what that kind of means is that what the multiplexer sees is the current input that we might want to store on there. And it's also going to see what it is currently outputting. That's being fed back. The D flip-flop is outputting. It's being fed back as input to the multiplexer. So then what that means is that with this load bit, if we set load to be 0, we're going to just simply take in the current value that we have, this is at 0, and not load anything new. A clock edge happens, and we just kind of keep restoring the same thing over and over again. But if load changes to 1, oops, I can't draw that. If load changes to 1, what that's going to do then is then take whatever is on the input to this bit chip we have, and then pass that through the mux and store that. So therefore, we have this kind of, it's kind of a self-supporting feedback loop. Typically, you don't want to do feedback ever in a combinational logic circuit. That's a bad idea. But we are showing how we can use this recursive kind of feedback idea to either support what we currently have and keep holding on to and maintaining a value, or we can load in a new value. And that's led us now to store a single bit of data. Super cool. That's not too bad at all. Once we can do this, everything's going to start building up on storing a single bit. So if this is that circuit we just designed, a single bit has the input, has the output, and then the load signal. Are we loading a new value, or are we maintaining the current value? We're going to zoom out. And then if we can load and store and load one bit, well, what if we combine multiple bits together so that now we can store some sort of in-bit number, like an 8-bit number, a 4-bit number, a 16-bit number. We just want to group them together and know that these are a number. Place value comes into play. Cool. Now we have some word of numbers coming in. We have a single load bit because we want to load all those at the same time or not. And of course we have then our output bit. The output bit's the word. All right, single bit. Now we have a word of bits we can store. And now what we want to do is start stacking this up farther and farther and farther. Our RAM chip is going to accept an input and an address. And so what we're saying is a RAM stands for random access memory. Random meaning we don't have to access all of the bits or whatever the storage addresses in sequential order. We can just say, give me address 10, now give me address 25, now give me address 2. It can be randomly accessed, not sequentially. Random access memory. So we have an address. That means a location where we're storing something. We want to put that on the address input, put the value you want to store. It will then store it to that particular address, and we can recall from that address later. And this is what I was alluding to in one of the earlier videos. The big key idea is the programmer, or even the user half the time, the user especially, but the programmer does not care where physically her data is stored on the particular RAM chip. It doesn't matter. As long as the memory chip can access that same location and bring it back, and it is not getting overwritten, then you don't have to worry about doing this in a very, very specific way. As long as one address maps to some spot in the memory and we can recall it, that's fine. The internal structure is actually not that important. It's an abstraction. So on the left, here is the abstraction that we are dealing with. We have a RAM chip of n different registers. So we have a single load bit. We have an input word of some n bits, and we have an address of k bits. An n and k, or I guess w and k, are different values. Keep that in mind. So we're going to go up to, let's see, RAM. So we have input is with w. It consists of n registers. Should be consistent here. So we have RAM n could be 64, whatever. We have address 0, 1, up to n minus 1 for a RAM n chip. Each of these is going to be a register that is w bits wide. Okay, so this could store, let's say if n is 64, we could store 64, and let's say w is 16. 64 is 16-bit numbers. Cool, whatever. This is our abstraction. We have an input, we have an address of some number of bits needed to access the n registers, and our output, which is always also going to be a word. So the structure we're going to look like, if you're stuck trying to think how to implement this, that's what's all shown on the right. Same kind of interface, in, address, load, and out. And then internally, kind of what we want to do is use a demux to kind of take our signals and translate those and connect them to the many different chips we have. And then we're going to be able to, what we want to do is be able to load a value onto one of these specific registers that the user is asking for right here. Load it somewhere up in this big array of chips and RAM storage registers, and then be able to pass that along to the output. This is a partial diagram. It doesn't have all the connections. It's kind of what your task is to figure out what to do. But the general structure is going to be a demux and a mux as long as we place an address, load whatever input value we want onto that address in some way, and it only needs to go to one register, and then we can recall it, and another address location, is not going to overwrite that register. Hopefully that makes sense. Once you have that very basic structure, if you've built up something like a RAM 8 chip, then your life starts to get pretty easy, because kind of what we've done in this class, we had a NAND gate, we built up a few logic gates, then we use that to build more logic gates, then we're using those to build up an ALU, and this, we're going to build up a bit, build up a way to store a register, and then build up a RAM chip, and from there it just starts stacking, stacking, and stacking. A RAM 64 chip is going to be made up of several RAM 8 chips. A RAM 512 chip is going to be made up of several RAM 64 chips. So you can kind of use this hierarchy, and to copy and paste 512 different registers. You can use the RAM 64. It's going to make your life a lot easier. The only really other confusing thing is we're going to create a specific register called the program counter. We'll talk more about that when we get into the CPU. Just know it's a slightly particular register because it has a couple different options. It's going to work just like a counter, really. So what we want to do, we want to be able to reset the program counter. And again, just think of it as a register that's essentially working as a counter. If we want to reset it, that means we want to set the value to be 0. So it's going to look at the 0th address. Typically, what's going to want to do is fetch the next instruction, and that just is caused by the program counter incrementing. And maybe if we have a go-to operation, we want to go to a specific instruction. That's just setting the address to a value. So that's why we're building this. It'll make much more sense when we start looking at the machine language of the CPU itself, but that's what we're going to do with that. You already have the components to build this, so don't overthink this too much. It's essentially a register with just a couple specialized functions. It has a 16-bit input, 16-bit output. It has load, because we may want to load a new value if it's a go-to statement. We have increment, which is going to be kind of the default, but that just means that increment by 1, add 1 to the number so we can go to the next register. And a reset just means store 0 into the program counter's memory. Think about using things you've already computed, like the ALU implementation. You have the pieces you need, and then think how you can work with those. It's fun to figure this one out. It's really not too bad at all. This is going to be a really important part of our component for navigating our CPU's code when we get to the next lesson. If you're stuck, I recommend looking at slide 56 of the Nand Detectors projects. If you go to their website, you can see the slides they have there, and that usually will try to help you. Good luck with this. This is a fun one. Once you get going, you can just build up and up and up, and at this point, you've just made a lot of pieces of a computer, so it's starting to get pretty interesting. So thank you very much. If you have any questions, happy to help.